So in the previous lecture, basically we have started over the next topic, that is your multiplexer, right? And we have discussed the basics of multiplexer. What is the meaning of multiplexer? What is 4:1 mux, right? 8:1 mux, right? And what is the meaning of input and the select line, and how you can find out the inputs from the select lines, and how you can design 4:1 mux, 2:1 mux, 8:1 mux, right? So in this lecture, basically we will discuss first how you can implement higher order mux using the lower order mux, right? After that, we will discuss why mux is or called as a universal logic or the universal circuit, right? So today we will start over the this topic, that is implementation of higher order mux using lower order mux, right? So the first example is how we can design, or how many 2:1 mux is needed to design the 4:1 mux, right? So how you can design this 4:1 mux using the 2:1 mux, right? So you all know about the 4:1 mux. In the 4:1 mux there are the 4 inputs, while in the 2:1 mux there are the 2 input. It means more than one 2:1 mux is needed to implement this 4:1 mux, right? So from here, if in the next I will tell you the shortcut how to find the number of lower order mux to design the higher order mux, right? First we will discuss the full implementation. You note in the 2:1 mux there is a one select lines and there are the 2 inputs, right? So I am giving these are your 2 inputs, I naught, I1, right? And this is your one output. And what is this output? And this is your one select line, right? So I am denoting this select line S0. So what is the expression? We already discussed in the previous lecture. Expression is S naught bar I naught plus S naught into I1, right? So this is your expression for the 2:1 mux, right? So you know there are the in the 2:1 mux there are the 2 inputs, right? While in the 4:1 mux there are the 4 inputs, right? So more than one is needed, right? So we can take one more 2:1 mux because and give this as a I2 and the I3, right? So now from here it is clear that this consists of the 4 inputs, right? I0, I1, I2, I3, right? So again I am denoting this as a S1, right? So similarly the output of this is basically, right? So you know in the 4:1 mux there are the 4 inputs. Now we can consider these 4 inputs of your 4:1 mux, and there is a single output, right? So if we give these 2 inputs, right? So first also you can design, you should know the output of your or the expression of your 4:1 mux, and you know the expression for 4:1 mux is, we already did in the previous lecture, S naught bar S1 bar into I naught plus S1 bar S naught into I1 plus S1 S naught bar I2 and S1 S naught into I3, right? So now accordingly we can give the values to the select lines, right? So now from here it is clear that this your 4:1 mux needed S naught bar S1 bar I naught, right? Similarly S1 bar S naught I1, right? So if I give here the S1, right, if I give here the S1, see, when you are designing the higher order mux from the lower order mux, in the first level you have to take the similar select lines, right? So here we can't take the S1, we have to take the S naught here, right? So S naught bar I2 and S naught into I3, right? So if we give these two outputs to the next 2:1 select line, 2:1 mux, and select line is S1. Now tell me what is the final output. We can represent this is the S2. Now this is your first input of 2:1 mux. This is your second input of 2:1 mux, and S1 is the select lines, right? So if we multiply, so if we take then S1 bar Y1 and S1 Y2, right? So what is Y1 and Y2? So Y1 is basically, and Y2 is this one, right? So now tell me, if we expand this, then this is the output of your 4:1 mux or not? Yes, this is the output of your 4:1 mux, right? This is your nothing but the 4:1 mux output, right? So now in the clear, if we are taking this as a black box, right? If we are taking this as a black box, means inside it consists of 2:1 mux, right? So it has the 4 inputs and 1 output, right? So this acts as a 4:1 mux. Now the question is, how many 2:1 mux is required to implement this? Now from here it is clearly seen that the 3 2:1 mux are required to implement this 1, 2, 3. Now the question is, if in the objective type examination, if this question is asked, then how you can find the number of the lower order mux, right? If you are going with the full process, then it takes a lot of time and it is also not suggested, right? So the I'm telling you the shortcut to find the number of mux here. In the second example, if I am taking how many 2:1 mux are required to implement 8:1 mux, right? So the shortcut is, this is 8 inputs, this is 2 inputs, right? This is higher order mux input, this is lower order mux input. So divide 8 by 2, it comes 4. Again divide this 4 by 2, right? It comes 2. Again divide this 2 by 2, right? It comes 1, right? Now this 1 is lesser than this 2. Now leave it up to here. Now if you take the sum of these, then it comes the 7. It means 7 2:1 mux are needed to implement 8:1 mux. Similarly, we can do here. Divide this 4 by 2, it comes 2. Now divide this 2 by 2, it comes 1, right? So total 3. So in this shortcut, by this shortcut, you can find the lower order mux using the higher order mux, right? So in the next example, if I am giving the next example here, how many 2:1 mux are required to implement the 16 into 1 mux, right? So similarly, divide this 16 by 2, it comes 8. Then divide this 8 by 2, it comes 4. Divide this 4 by 2, it comes 2, and divide this 2 by 2, it comes overall 15 2:1 mux are required to implement this 16 into 1 mux, right? So now in the other words, specifically for 2:1 mux, right? Specifically for 2:1 mux. So now we can give more example to you. How many 4:1 mux are required to implement this 16 into 1 mux, right? So again similar method, divide this 16 by 4, it comes 4. Again this divide 4 by 4, it comes 1, right? So 1 is lesser than 4, so leave it up to here. So 5 4:1 mux are required to implement this 16 into 1 mux, right? So next example is 64 into 1 mux. How many 4:1 mux are required to implement this 64:1 mux, right? So similarly, divide this 64 by 4, 16. Divide this 16 by 4. 4. Divide this 4 by 4. It comes 1. So total 21. Right. So in this way, any question can be asked regarding this. For example, like 256 into 1 marks. How many 16 into 1 marks are required to implement this? Right. So divide 256 by 16. It comes 16, and divide 16 by 16, it comes 1. Means the 17 16 into 1 marks are required to implement this, right? So this is the shortcut to find the higher order marks using the lower order marks. So next we will discuss why mux is behaves as a universal circuit, or why mux is called the universal logic, right? It means with the help of mux, other gates can be implemented, right? So that's why it is called the universal logic. Like we can design the AND gate using the mux. We can design OR gate, NAND gate, XOR gate, NOR gate, XNOR gate, or any Boolean expression we can design using over the multiplexer, right? Whether the multiplexer may be 2 is to 1 mux, 4 is to 1 mux, right? This is 2 is to 1 mux, and this is its truth table. Now first, how you can design the NOT gate using 2 is to 1 mux, right? So from this 2 is to 1 mux, it is clearly seen that when the select line is 0, output is this first I note, right? When the select line is 1, this output is I1, right? So here, if I am saying if the select line is A, right, and I naught is 1 and this is 0, right? So here the method for this is the NOT gate, right? And I am saying A is the input, Y is the output, right? So if A is 0, output is 1, and if A is 1, output is 0, right? So from here we can say if your select line is 0, output is I naught, select line is 1, output is 1, right? So this is now your, these outputs are now your act as your the inputs here, and here the we can say is your select lines, right? So we can write the expression for this now. This is 2 is to 1 mux. You know the expression for this 2 is to 1 mux. This is your select line. So A bar into what? 1. Next we can write A into 0. This is your 0, right? And this Y is here basically what? A naught. Now it behaves as the NOT gate or not? Yes, it behaves as the NOT gate now. So now we will discuss how the 2 is to 1 mux behaves as the AND gate, right? So you know the truth table of AND gate, 0 0. So this is the truth table of your AND gate, right? And you know this is the truth table of your 2 is to 1 mux. Now tell me, here if I am taking A as a select lines, if A is 0, what is the output? Output should be 0. If A is 1, what is the output? We can say this is your B, this is your B, right? So from here, I think so now it is clear to you. From here, now it is clear which one is the inputs and which one is the output. If I am taking A as a select line, right? And if A is 0, what is the output? If A is 0, what is the output? Output always 0. Output always 0, na? So we can take this as a 0, right? Or other words, from here, if A is 0, output is 0. If A is 1, output is 1. And this is your inputs, right? So 0, B is your inputs. Like this you can find out. This 0 and B is your inputs and this is your output. Now this behaves as the AND gate or not? Yes, this behaves as your AND gate, right? So this is what? Nothing but your AND gate, right? So similarly, you can find the, or you can design the OR gate using the 2:1 mux. So first you should know the truth table of your OR gate, and you know this is your truth table of your OR gate, right? This is truth table of your OR gate and this is your truth table of your 2:1 mux, right? So now if S is 0, or we can say the A is 0, what is the output? Output is your B, right? If A is your select line, so we can say S is 0, this is your select line. And if A is 1, if select line is 1, what is the output? It is always 1, right? So in terms of A and Y, we can write if A is 0, output is B. If A is 1, output is always 1, right? So now these are your inputs of 2:1 mux, right? This is the way to design this these gates from this 2:1 mux, right? So this is 2:1 mux, this is B, this is 1 and this is A, right? So also you can write the expression for it, right? This is basically your what? A bar B plus A. If you solve this, then this is nothing but A plus B, right? So in the objective type, I can ask number of mux requires to implement OR gate. Only one mux is required to implement OR gate. Number of mux requires to implement the AND gate, right? One mux, number of mux requires to implement the NOT gate. One mux, right? So now we comes to our NAND gate. You know, this is the truth table of your NAND gate, right? And you know, right? So now tell me, if I am taking this A as a select lines, right? If A is 0, output is always 1, right? And if A is 1, what is the output? It is your B bar, right? So we can take this is your B bar. Now this act as your the inputs of your 2:1 mux, right? But now here this is your B bar, right? And you have to implement completely this NAND gate using the 2:1 mux, right? So this is your I0, I1, and if I0 is 1, I1 is B bar, and this is your A, and this is your output Y. Now this is your B bar, right? So we can't directly take the B bar as the input because only A and B is available here. Now if you want to take the bar of this, if you want to take the bar of this, then again you have to use one more 2:1 mux, right? Because one for the NOT gate you have to require one 2:1 mux, right? So this mux is added here, right? So for this NOT gate, one extra mux is needed, right? For this NOT gate, one extra mux is needed here, right? Then only it can becomes the B bar, right? So number of mux requires to implement the NAND gate. Now it is not 1, it is 2. One for this NOT gate and one this for the other logic, right? So now for the NAND gate, number of mux, 2 mux are required to implement this, right? You can write the expression for this A bar dot A and this A B bar, right? So this comes A bar plus B bar. This is nothing but AB whole bar. So this is what? This is your NAND gate, right? So 2:1 mux are required to implement this NAND gate, right? Next comes to NOR gate. So you know the truth table of your NOR gate. Right. If I am taking A as a select lines, right? If A is 0, what is the output? Output is your B bar, right? So this is B bar, right? If A is 1, what is the output? Output is always 0, right? So now these are the inputs of these two numbers. Now similar to NAND gate, now here is a one NOT gate, right? So this is your one B bar. So for this B bar, we need one extra 2:1 mux, right? And this is your 0, this is your A, right? And this is your Y. So number of mux required for the NOR gate, number of 2:1 mux required for the NOT gate, it is your 2, right? So similarly, we can design our next gate, that is your XOR gate, right? And here you know the truth table of your XOR gate 0 0 0 1 1 0 1 1, right? So this is 0 1 1 0, right? So this is your XOR gate. If I am taking A as a select lines, right? If A is 0, what is the output? Output is your B. If A is 1, what is the output? Output is B bar, right? So how many mux are required for how many 2:1 mux are required for this XOR gate? So this is your B and this is your B bar and this is your A and this is Y, right? And the if you write the Boolean expression for this, then it becomes A bar B plus A B bar, right? So one extra mux is required for this B bar, right? So 2:1 mux are required to implement the XOR gate, right? Now we comes to your XNOR gate. So this is the truth table of your XNOR gate, right? So if A is 0, what is Y? It is your B bar, right? So this is opposite of this B now, so that's why it is your B bar. If A is 1, what is the output? Output is your B, right? So now this acts as your inputs. Because in the mux, see, output is nothing but the selection of the inputs, right? So this is your B bar, this is your B, and this is your A, and this is your Y, right? So 2:1 mux are required to implement the XNOR gate, right? So now the question is that I told you in the first of this combinational logic, this is your half adder. So how many 2:1 mux are required to implement the half adder? Can anyone tell me? You know the half adder. This is your half adder and these are your two inputs of half adder. What are the outputs? Sum is basically A XOR B and carry is your what? AB, right? So how many 2:1 mux are required for this? Yes, 3, right? So two for this XOR gate and one for this AND gate, right? So these questions can be asked in your exam. Similarly, for the half subtractor, 3:1 mux are required to implement the half subtractor, right? Clear? And if I am saying design a half subtractor using 2:1 mux, right, then it is also simple. It is also simple. So using 2:1 mux, first design this XOR gate, right, and then after that design this A bar B, right? Clear? So this is your half subtract, right? So how you can design A bar B? How you can design A bar B using 1:1 mux? How you can design? So first, this is your select line if I am taking. Then what? Here I can take B and here I can take 0. So what it is A bar B. Don't think always that for this bar you need one extra. Here A can be act as the select line. So you have to think in this manner, right? So now this is A bar B. So for the half subtractor also 3 2:1 mux are required to implement this. Okay, so now we will implement all these gates, or I will tell you how to implement all these gates using the 4:1 mux. This is nothing but in the similar way you can design all these gates using the 4:1 mux. You know, see, in this previous discussion, you know, over the basic gates, NOT and OR, only 1 2:1 mux are required, right? We can also use for this AND gate or the OR gate, we can also use over the 4:1 mux, right? So accordingly, your input can be changed for that, right? So if we want to design your AND gate using the 4:1 mux, right? If you want to design AND gate using 4:1 mux, then how you can design? See, you know the truth table of your AND gate. This is 0 0 0 1, right? So now here, you know, in the 4:1 mux, there are the 4 inputs and there are the 2 select lines, right? So now you have to think. You have to design the AND gate using this 4:1 mux, right? So these act as now your all the inputs, right? And what are the select lines? Select lines is your AB, right? So if we are taking first 3 terms becomes the 0 and in the last AB dot 1. This is your nothing but your AND gate, right? Similarly, in the similar way you can design the XOR gate, right? So in the XOR gate, you know the truth table of your XOR gate is in the XOR gate. What is the output? This is your truth table, right? So here in the XOR gate, this act as your the inputs, right? So this is your XOR gate, right? With the similar this select lines A and B, right? Similarly, you can design the XNOR gate, right? In the XNOR gate, you know the truth table is this and this act as the inputs for the XNOR gate. For the half adder, how many 4:1 mux are required to implement the half adder? No. Now from here, from this discussion, it is clear that only one 4:1 mux is required to implement XOR, one 4:1 mux is required to implement XNOR, right? One, uh, see, in the previous 4:1 mux, 2:1 mux are required to implement XOR, XNOR, right? So, NOR gate, NAND gate, but here for all these NOR, NAND, only one 4:1 mux is required to implement this, right? So now for this half adder, how many 4:1 mux are required to implement? 2, right? So 2 is the right answer. So 2 4:1 mux are required to implement this, one for the sum, one for the carry, right? Similarly for the half subtractor, how many 4:1 mux is required? 2 4:1 mux is required, one for the difference and one for the borrow, right? So Now, based on this discussion, I want to give some examples, right? So you have to tell me the answer of all those examples. So first is, this is your 1 mux circuit is given. This is 4:1 mux is given to you, and these are your select lines B, A. This is basically S1, S1, right? I0, I1 is connected combinedly to C bar. I2, I3 is connected to basically your C. So find the minimize expression for the output Y. Options are basically A XOR B, A XNOR B, yes. This is the question. You have to find out the minimize expression for the output Y. You know how to write the expression for this output Y. You can easily write what comes first. A bar, B bar, dot. This I naught. This is general expression for this, na? Right? So what comes? I am directly writing this I naught is your C bar and this I1 is your C bar, right? And what is your I2? I2 is your C. So now it is asked a minimize expression, right? So now further you have to minimize this, right? So after taking common from in between these two terms and these two terms, what is? What is your A bar C bar? If you take this A bar C bar common, then inside it is B plus B bar, and B plus B bar is basically nothing but 1. Similarly here we can take the AC common, it becomes the B plus B bar, right? So this is AC plus A bar C bar, right? So this is nothing but A XNOR C, right? So this D is your right answer, right? Also for the minimization, there is no hard rules. You have to use the Boolean expression. You can also use the K-map. It depends on you. In which you are comfortable, you can use that, right? So in the similar way, we want to do the next question based on all this discussion. So this is your question. You have to minimize this expression. This 4:1 mux is given. This is C naught. This is 0. This is 1. This is C. Right. And this is your A. This is your B. And this is S naught. S. Right. So you have to minimize for the output Y. Right. So here I am directly writing the answer. Answer of this question should be AC plus B bar C. Right? Directly you can write this first Y, the expression for the A bar, B bar into I naught. Here the I naught is C bar and the so on, and in the last terms A, B, C. Right? Then further you can solve after minimization. This is your output of this function. Right? So one next question I want to give for the practice. You can do the practice of this question at your home. Similarly, these two select line is given and four inputs are given. Four inputs are CD, C bar D, D1, right? So this type of inputs can be given, right? So now what is the first output? If both A and B 0, that is your A bar B bar dot CD, right? Now here the CD is your I naught, right? Next, yes, in the next, what we can do? A bar B D, right? Similarly, A, B bar, D. Next, A, B, note 1, right? Now further you can solve this, right? So this is all about this example. So students, if you have any doubt related to this topic, then you can send me a mail or you can contact me directly. So for more video update, please subscribe this channel, fine, so that every information regarding your course or regarding this digital electronics lectures you can get easily. Fine. Thank you for your attention.